Section 4.3 is on derivatives and how they give us information about shapes of graphs, page 1. So in section 4.1, we talked about critical numbers. And this is a point on the function, specifically an input value, where the derivative is equal to 0 because you have a horizontal tangent line, or the derivative does not exist because there is no tangent line. At that time, we discussed that local max and mins, so not necessarily absolute, but local max and mins can only occur at critical numbers. So these are important values to find. Specifically, let's look at the first derivative test. This is where our intervals change from increasing to decreasing. If the derivative is greater than 0, which means it's positive, then the interval is increasing in this region. And the reverse. If the first derivative is less than 0, where less than 0 means it's negative, then our function is decreasing in this region. This leads to the first derivative test. So we're going to have some critical number c, because our first derivative was 0 or did not exist, on a continuous function. If the derivative around this critical number changes from positive to negative, then it's going from increasing to decreasing. And if you're going uphill to downhill, then you have just passed a local maximum. Or the reverse. If values around the critical number in the derivative change and change from negative to positive, they go from downhill to uphill, then we have just passed a local minimum. Now, keep in mind, when testing points around a critical number in the first derivative, sometimes you're not going to notice a change at all. You're walking uphill, you stop, and you walk uphill continuously. So you may have had a flat point, or even a flat point where you're walking downhill, but this means there is no local maximum or minimum at this critical number, even though it's still a first derivative of 0 or does not exist. Here's how we put this all together in a single problem. We are given a specific function, and we're asked to find intervals that are increasing and decreasing, which are given to us in our answer box, and the coordinates, that means the x comma y value of local maximums and minimums, which for plural we'll call maxima and minima. Well, the only place that I can get my maximum and minimums and determine increasing and decreasing is by focusing on the critical numbers. This is where I'm going to find the first derivative, so taking the derivative of my function, and I'm going to set it equal to 0 if there's a numerator, and the denominator would also be set equal to 0. Notice this is x cubed. That means it's a third degree polynomial, so I should be getting 3 roots. And as you can see below, I get 0, and then both positive and negative 2. I do get 3 different roots. The best way to solve a problem that has x appearing more than once, and you can't simplify by adding or subtracting them, is to factor out the GCF, the greatest common factor, which in this case, we can divide both terms by a 4x, leaving us x squared minus 4. Because there is an x in the first term, I can set it equal to 0 to find the variable is 0. And the second term, degree 2 polynomial, means I should be getting 2 radicals. Sorry, I get 2 radicals. I should be getting 2 roots. Because I only have x once, I didn't have to factor, but I could have factored this into x plus 2, x minus 2. Hopefully you're enjoying the dogs barking, and whoever's at the front door will be leaving soon. I'm not starting over. Okay, so now we're ready to use the first derivative test. Even though we found the first derivative, that wasn't the test. That was only to get the critical numbers. The first derivative test asks us to take the number line, in our case from negative infinity to positive infinity, to take all 3 critical numbers and put them in numeric order. Negative 2 comes before 0, which comes before positive 2, which comes before positive infinity. Therefore, I can take those critical numbers to find intervals that my graph is divided into. And after finding my intervals, I want to test some number within those intervals in the derivative. So it's important that I have my f prime where -3 is in my first interval. -1 is in this interval, +1 and +3. I lucked out. I got whole numbers. You may have to choose decimal numbers. Now, ultimately, if you remember, we just care about being greater or less than 0. But when I plug -3, I chose to plug it into the factored form so that I had 4 times -3, which is -12, but I really cared that it was negative. When I plugged -3 into x squared minus 4, -3 squared is +9, but 9 minus 4 is going to be a positive number. And because a negative times a positive is negative, this interval is decreasing. And so I'm actually just going to work from that lens. I'm going to take -1, which is going to make the first term negative. Even though the -1 is squared in the second term, it's still smaller than 4. So I'm going to have a small number -4 to give me a negative, which multiplies to a positive. So this interval is increasing. +1 is going to give me a +4. 1 squared is still 1, -4 is still negative. So they're going to multiply to be a negative, which is decreasing. But +3 will give me a positive first term, but 3 squared is +9, and remember that gave me a positive. So I've got increasing. So ultimately I'm ready to answer my questions, but there's 2 more things I want to do. First, we had mentioned above, if it changes from increasing to decreasing in one interval to another, then in between these intervals, I'm going to have a relative minimum, and we said minimums can only occur at the critical numbers. Using this increasing again, I'm changing from increasing, which is going up, to decreasing, which is going down. So I have a relative maximum, and using that decreasing again, downhill to uphill, gave me a minimum. So I know where my max and minimum x values occur. Whoops, one of these should have been positive, right? Sorry about that. But I also need those coordinates because the directions ask for the coordinates. So I knew that 0 and positive and -2 were my critical numbers, but I had to go back to the original function to plug them in to find their y values. Intervals of increase is my first answer box, and I've highlighted those intervals in green, where intervals of decrease I've highlighted in this tan color. My local maximum, I only had one maximum, which was at 0, and we already said its y value, its coordinate, not its interval, is +10. And for the local minimums, we had -2, which has an output of 6, and the second one should be +2 with an output still of -6.